timer for 15 minutes.
I think soccer class is also really fun.
Not 15.
I think yours is funnier though. By a landslide, yours is way funnier. Relax.
I'm sorry, Corwin, who asked you who class was funny?
No one asked, I'm just giving my opinion. It's true, I won't deny it. I won't deny that I take full rabbits in the middle of my lap. They make fun of me for being super friendly.
No, turn red as your sweater.
Okay. All right, let's get going. We gotta finish this. Okay, so let's figure out which one of these is growing at a faster rate. We're taking a look at questions 10 and 11 right now. So question 10, we have natural log of x and cube root of x. Any guesses which will be faster? They're both pretty slow.
Which is the fastest?
X, like cube rad x. If I had to pick.
Get the cube roots faster?
If I had to pick.
Okay, well let's try it. So we have natural log of x and the cube root of x. Okay, I like to have you think about which one grows faster before you even start the problem. It kind of builds that instinct, that mathematical part that you need to get activated at some point. So we think this one's going to go faster. So I'll put it on the denominator. Okay. And I notice that the form here is infinity over infinity. So we're going to L'Hopital. We get the limit as x approaches infinity. 1 over x. See, the derivative of the cube root of x is x to the 1/3. So that's 1/3 x to the negative 2/3, right? Let's simplify that. That's the limit as x approaches infinity. 1 over x over 1 over 3 times the cube root of x squared. Let's simplify that again. That's equal to the limit as x approaches infinity of 3 times x to the, I don't know why I did that, I should just keep that as 2/3 power, over x. Simplify that one last time. That's the limit as x approaches infinity of 3 over x to the 1/3 power. As x goes to infinity, this goes to 0. Therefore, the cube root of x grows faster. Natural log of x grows to infinity, but it gets to infinity at an excruciatingly slow pace. Super slow. Yeah?
So if it had equaled infinity, ln of x would have been faster?
Yes.
Okay.
Then that's
And if you would put g of x, if you would put the cube root of x on top and it had equaled infinity, then g of x would have equaled faster still?
When you say g of x, you mean the numerator or denominator?
Hold on.
He's saying if you switch them in the beginning
Mm-hmm.
and then you ended up with 0, then
It's kind of a weird question because I wouldn't have ended up with 0. If I switch it, I'm going to end up with infinity.
okay, so if you end up with infinity, then that would prove that.
The numerator is faster.
I'm wrong.
Okay, so if it's infinity, then the numerator is.
Yes.
Got
No matter what?
No matter what. If
Okay. Great.
No. You can only use L'Hopital's rule if you have an indeterminate form.
Yeah, I'm saying like if it keeps coming up as an indeterminate.
Yeah.
form.
Yeah. If it keeps coming up
So it's like a
indeterminate,
normal limit like that,
that's the way L'Hopital works. Keep going until you get something that's not indeterminate.
and it'll either be 0 or infinity.
Last one of this section. We have x or x plus 1 over x. Well, that's kind of a weird question, right? Can I turn that into x or x squared plus 1 over x? Which one do we think grows faster? Which one do you think grows faster? You think x is faster? Okay, let's check if x is faster. We'll take the limit as x approaches infinity of x squared plus 1 over x over x. Okay. You might be tempted to go ahead and start taking L'Hopital's rule now. Don't do it. Simplify. You might be tempted to use L'Hopital's rule here again. You don't need to. This is a polynomial over a polynomial. Both polynomials have the same power. 1 over 1 is 1. Therefore, they grow at the same rate. You were getting ready for like 3 L'Hopitals, weren't you?
Well, so how do we, so like when it's 1, it'll be the same rate.
When it's any constant, it's the same
Like
rate.
1, 2, 3, 4.
Any constant. Any constant. Okay. Okay, previous section, we have L'Hopital's rule to evaluate 3 limits. Let's take a look at those 3 limits. Limit number 1, which is question 7. We have the limit as x approaches 0 from the right side, sine x over x cubed. Let's check and make sure this is L'Hopitalable. If I plug in 0, I get over 0. So that means I can use L'Hopital's rule. Always check to make sure you can use L'Hopital's rule. So let's do the LOP. And we take the limit as x approaches 0 from the right. The derivative of sine is cosine. The derivative of x cubed is 3x squared. Let's see if I can use L'Hopital's rule. Cosine of 0 is 1. Oh, I'm done. No more L'Hopital for me.
This is gonna sound kind of stupid, but I never understood like how you got the 0, 0, 1, 0, like
Plug in.
infinity 0.
Plug in 0.
Okay. See, I told you it's nice.
All right, we're getting, okay, the numerator is getting close to 1, right? Is it positive or negative? Positive. Is 3x squared positive or negative? Positive. Okay, so this is going to go to positive infinity. Remember, constant over 0 goes to one of the infinities.
It's positive because the cosine and 3x squared are positive.
Mm-hmm.
And if one of them is negative, negative,
Yep. Exactly right. Question 8. Oh boy. I think we should prepare ourselves for this.
Is it another full pager?
Oh, I don't know. 4-pager. We did not do.
Full pager.
Oh, you've not done anything here for 4 pages yet.
Yet?
Any spoiler alerts there?
Well, if you write big, I mean,
Roya.
I did it, yeah. It was like number 22.
You've made it 4 pages.
Roya
I'm
writes
sure.
huge.
I've used
Well, not like 4 pages front back.
Oh, you're right.
I write really good. It's really bad.
okay. Y equals. Oh, we should look at the L'Hopital form here.
It's okay.
That's infinity or to the 0 power, right? Infinity to the 0 power. That's definitely one of the mysteries of life. So y equals 1 over x squared to the x power. Natural log of y equals x times the natural log of x to the negative 2 power. Is that good? Is that good for you?
Yeah.
Okay, that's awesome because now I can make this negative 2x natural log of x so much better. I'm just simplifying right now. The limit as x approaches 0 for the natural log of y is equal to the limit as x approaches 0 for negative 2x natural log of x. Let's check our L'Hopital form. This is plug in 0 here and you get 0. Plug in 0 here, you get negative infinity. Certainly. We're going to prepare this for L'Hopital. Limit as x approaches 0. You want that negative 2 on the numerator or the denominator? Kind of like it on the numerator, actually. You could have done it. You could have put it anywhere. It's just that you're already using the... I'm fearful that you won't make this 1 over negative 2x. That's what I'm fearful of. So I try to keep that denominators, whenever you're doing this inversion, I try to make that as clean as possible, as few constants as you need.
So we don't have to bring it down, but it's good to bring it down because it's safer.
The constant?
The 1 over x.
No, you have to bring that 1 over x down. Yeah. Otherwise, you can't L'Hopital. Okay, so we have an infinity over infinity form. We can L'Hopital now. That's, oh, that is the ugliest 0 I've ever written. 0. Negative 2 over x over negative 1 over x squared. Don't try and do anything. Simplify. I think I get 2x here, don't I? So, the limit as x approaches 0 of the natural log of y is equal to 2 times 0 or just 0. Therefore, the limit as x approaches 0 of y is equal to e to the 0. Therefore, the limit as x approaches 0 of 1 over x squared to the x power is equal to 1. That is not the worst one we've done. That's actually pretty nice. The trick here, though, is to change that from natural log of 1 over x squared to x to the negative 2 power.
Mr. Ray, what if I solved that a different way but I still got the same answer?
I'd be worried. Sure. Good? Okay.
Out of curiosity, is this gonna be no calculator?
No calculator. I can't look at it now. Okay, let's take a look at 9. Nine, limit as t approaches 0, 1 over sine t, minus 1 over t. Let's check our L'Hopital form. We get 1 over 0, which is infinite, minus 1 over 0, which is also infinite. Yay! So good. Limit as t approaches 0. We're going to put this all to a common denominator. T minus sine t over t sine t. LCD. Let's check our L'Hopital form, our indeterminate form. 0 minus 0 is 0. 0 times 0 is 0. I'm free to use L'Hopital's rule. L'Hopital. Limit as t approaches no, not infinity. 0. 1 minus cosine t over product rule. Oh, lovely. 1 times sine t plus t times cosine t. Not so happy with that. I think I want to clean that up. Let's see. The limit as t approaches 0 of 1 minus cosine t over sine t plus t cosine t. Now let's check L'Hopital's form, our indeterminate form. We have 1 minus 0. No, 1 minus 1 is 0. Oh, don't tell me.
Please don't.
Sine of 0 is 0 plus 0 times.
No, yeah.
Yeah. Let's do it again.
First time.
Yeah. Limit as t approaches 0. See, what's the derivative of cosine? Is that negative sine? Negative sine. The derivative of sine? Cosine. The derivative of t cosine? Product rule. Okay, I'm feeling good about this one. Limit as t approaches 0, sine t over 2 cosine t minus t sine t. This is good. This is good. Let's plug in 0. What's sine of 0? 0. What's cosine of 0?
1,
Good. 2 minus 0 times 0. 0, which is 0. The limit as t approaches infinity of 1 over sine t minus 1 over t equals 0.
Limit of as t approaches 0.
Limit as t approaches 0. Thank you. Oh, this time infinity minus infinity was 0. That's kind of, wait, think,
That would be the thing that could be.
no.
No, that makes sense.
No, it's different every time. This time we got 0, but even more profound than 0. We're saying that the 0 or the infinity that you get of 1 over a trig function is the same infinity you get as 1 over t.
Mathception. Calcception.
And I think I know why.
Why?
I don't think I'll ever know why.
I don't think I want to know why, but we're actually going to see the reason why in chapter 9.
Can we have a preview?
That's like at the end of an episode of a show when it says to be continued. The most frustrating thing ever.
No,
How-
when they have like on our next episode.
No.
Just remind us. They have like scenes from our next episode. Infinity minus infinity equals 0.
We'll probably all say. It's like dying right now.
Rena, your hair, you look like you're homeless.
Are we still continuing?
Okay.
I don't even, I'm not even.
Let's keep going. Question 6. I have half an hour until my timer runs out. I think we can finish this in half an hour.
Yes.
What?
Okay. So we have 6. B is equal to 2n minus 1 over 3n squared plus 1. Okay. Now this sequence of numbers, does this actually approach a limit? Why don't we see that? Let's start plugging in numbers. Let's do the first 5 or 6. Let's plug in 1. What do we get? 1/4. Good. Let's plug in 2. What do we get?
413.
3 over 13? Let's plug in 3. 5 over 28. Let's plug in 4. 49.
Bye, Mr. Fred.
Bye-bye. Have a good weekend. Does this seem to be approaching anything? It does look like the denominator is growing a lot faster than the numerator, doesn't it? So if that does let me know that I'm probably going to go to 0. Let's check what is the limit as n approaches infinity of 2n minus 1 over 3n squared plus 1. Remember, there were 3 ways of doing this limit.
Yeah. Use the first term.
Yeah,
Is it equal 0?
Because of the thing exponents.
You can't use exponents.
yeah, you could just use exponents. 0. There we go. Yeah.
So on the test or on the AP test, are they gonna expect us to write out the first few terms of the sequence?
They're not going to expect you to, but it's a good idea on a lot of questions.
Okay. Would they ever ask, like, please write the first four?
You won't get credit for it. But
Not
you
even-
also,
Not even if they do it like as a part A, it's like a first part A.
they would never do that as a part A.
It's too easy.
Too easy.
Plugging in mental math.
Yeah. Yeah. Yeah.
Well, you might run out of fingers at some point.
Each AP test is roughly 4 hours.
No, it isn't. No.
It's somewhere between
5.
Oh, no.
Okay, 5 is actually kind of, 5 kind of, well, I don't know how to describe this. Some years we talk about we do this better than other years. This year I don't think we did this all that great. 12 over 48 and 15 over 240. And the way I want to consider this is I want to take a look at the sequence of the numerators and the sequence of the denominators separately. Okay? Let's take a look at the numerators. And let's number them. I meant to write numerator. We have 3, 6, 9, 12, 15. This is the first one, this is the second one, this is the third one, this is the fourth one, this is the fifth one. Do you see a relationship between this number on top and the number below it?
You're adding 3.
You're multiplying by
I want an explicit rule. Explicit
that's-
rule.
So A1 plus and minus
AN.
1D.
AN equals AN minus 1 plus 3.
That's a recursive rule.
No.
Sorry.
Isn't it just n times, isn't it 3n?
Just 3n. My numerator is always just going to be 3n. What about the denominator, though? This one. Good luck here. Is it an? Denominators? Annators? I?
Oh, I get it. So it's 2, you multiply 2 by 2, you get 4. You multiply 4 by 3, you get 12. You multiply 12 by 4, you get 8.
What is
No, wait, that makes sense.
Okay. The point here is we need we can't use a recursive rule. We have to use an explicit rule. Okay? So this seems pretty good. 1 times 2 is 2. 2 times 2 is 4. 4 times 3 is 12. 12 times 4 is 48. 48 times 5 is 240. Did you see that? The zigzag rule?
Yeah. I see.
The zigzag rule?
It's n.
It's pretty cool, right?
How'd you figure that out? I mean,
I would have left figured that out.
I figured that out, but I didn't know what it was called. And then I looked at
Well,
it was
okay, Mr.
Here's the problem. That method right there is good for a recursive rule. It's not good for an explicit rule. Okay? So we gotta talk. This 2 is 2, right? This 4 is 2 times this, right? This 12 is 3 times this 4, right? This 4 was this times this. So this 12 is 3 times 2 times 2.
Wait, is it? Oh.
48 is 4 times 12, right?
But it's also 4 times 2.
Which is like 4 times 3, 4 times 3 times 2 times 2. Let me make this better for you. 4 times 3 times 2 times 1 times 2.
great.
This 240 is
5 times 4 times 3 times 2 times 1 times 2.
What do you call this? 5 times 4 times 3 times 2 times 1.
Factorial, 5 factorial.
That's 5 factorial. These are n's, right?
Why is that a 2 though?
We had to start off with that too. Let me tell you right now. I'm not going to. I'm going to be really clear about this. It's going to be really good for you to remember the first 5 factorials. Shh. Good pro tip. Pro tip. Learn the first 5 factorials. One, 2, 6, 12. No. 1, 2, 6, 24, and 240. 1, 2, 6, 24, 240. Okay. When you see that pattern, you know it's factorial. Yes. 1, 2, 6, 24, 120.
So that's just n.
That's n factorial.
I wonder if that'll end up on that.
No, wait.
Okay, that takes care of this. No. The formula is for the answer. The formula for the answer is 3n over 2n factorial.
Wait, is it 240?
If it's like 4n over 2n factorial, can we just make it 2n over n factorial?
That was a yes. It's okay. 4. Let's determine if the sequence converges or diverges. We have an equals -1 to the n plus 1 over n squared plus 2. Okay. So I'd like you to remember that we said that if absolute value of a sequence converges to 0, then the sequence converges to 0. Do we remember this? If the absolute value of an converges to 0, then an also converges to 0. That was that theorem. We used it when we want to talk about series that alternate, like this series does. Mm-hmm. Yeah?
So we can't do the regular exponent rule that we do usually?
Not yet. Okay, so let's see. Absolute value of an in this case is equal to the absolute value of -1 to the n plus 1 over n squared plus 2. And that's just equal to n plus 1 over n squared plus 2. Now we use that rule. The limit as n approaches infinity of n plus 1 over n squared plus 2, this is equal to 0.
Because it's squared.
It's n over n squared. Mr. Maria,
Mm-hmm.
what would happen again if it was like n squared over n?
N squared over n would go to infinity.
Okay, and then n squared and n squared, the coefficients.
Would be the coefficients, yeah. We're so close. Question 3. The second and fifth term of a geometric sequence are 1/2 and negative 32. I'm going to stop right there and just write that down, okay? A2 equals 1/2. A5 equals negative 32. How many r's do I need to multiply to get to 32? But never mind. Let me start this over again. A2 was equal to A1 times the ratio, right? Is it ratio squared? No, ratio. And that's equal to 1/2.
This is the recursive rule.
This is the explicit rule. A5 is equal to the first term times r to the fourth power, and that's equal to negative 32. We're going to be working from here. Can't I regroup this as A1 times r cubed? I could do that, right?
Yes.
A1 times r is 1/2. 1/2 times r cubed equals negative 32. R cubed equals negative 64. Therefore, r, I believe, is negative 4.
Yes.
Okay, that should take care of at least one part, right?
How come you could leave it like that? A1 times r,
Mhm.
r cubed. How can you do that?
Oh, r to the fourth power is just r times r cubed.
Yeah, then wouldn't you?
So A1 times r cubed. Just group the first two.
Okay. Oh, okay.
We should figure out what A1 is now too, right? Okay, so A1 times r, which is negative 4, equals 1/2. Spoiler. A1 therefore is negative 1/8. Okay, part A, sixth term.
Wait, so
A6 is equal to A1 times r to the fifth power, which is equal to negative 1/8 times negative 4 to the fifth power. Let's see, what's negative 4 to the fifth power? Negative 4 squared is 16. 16 squared again is 256. 256 times 4 is 1028.
24.
1024, yeah. So this is equal to negative 1/8 times negative 1024. Hmm?
So, without a calculator, we actually have to find out what.
Yeah, why not? 4 to the 5th power? It's easy.
Okay.
But that's
Yeah,
not
come.
that's scary. But that's not what we do.
8 into 10 one time. 8 into 22.
Yes, correct. Wait, what's no calculator test?
Yeah. 2 times. 8 into 44. 5 times.
It's 128.
Yeah.
What did I do wrong?
Uh,
8 into 10 is 1. 22, 8 into 22 is 2.
And then 8 to 64.
8 into 64 is 8. Yeah. B. What is B? Find the common ratio. Sweet. Common ratio is negative 4. C. Find the explicit rule for the nth term. A1 was negative 1/8. Negative 4 to the n minus 1. I'm going to simplify that. Negative 1/8.
See, this was an FRQ question, did you have to simplify it?
No. Is there a D? Recursive rule. Recursive rule. What was the first term? Negative 1/8. And then AN is equal to negative 4 AN minus 1.
So the recursive rule is R A N minus 1.
One more time.
The recursive rule is R A N minus 1.
RAN minus 1.
Never mind. I think
Okay.
You know?
Yeah.
Okay, wait. There's no way to like plug this into our calculator and get an answer, right? Like we have to do it by hand,
No calculator.
right? So like if we can't use a calculator to cheat, why can't we use a calculator on the test for like basic stuff that to save time?
Yeah, because you wouldn't get a calculator for this.
Okay.
I mean, on an AP test.
Yeah,
It
okay.
would not be this is not the calculator portion of the test. Never will be. And to answer your question, yes, you can cheat with this part with the calculator.
Mhm.
Oh, yeah.
You can cheat on it.
I forgot to ask you this time. Do you know how many free response and how many multiple choice there are?
10 and 2, normal test.
Okay.
So 50-50?
50-50, yeah. Okay, 2 more. What are we supposed to do for these? A, B, and C? What is this? 15, 13? Wow. 15, 13, 11, 9. Okay. All right, so I think you can see that we are just decreasing every term by 2. So A Recursive rule. Don't forget the first term. First term is 15. Each term is equal to the term before it plus negative 2. Okay. And part B. What is the explicit rule? The explicit rule is Bn equals B1 plus n minus 1 times D, which in this case is 15 plus n minus 1 times negative 2. And that simplifies into 15 plus 2 is 17. 17 minus 2n.
Yeah, that's B and equals, right?
Oh yeah, Bn. That's supposed to be an n. Part C, the ninth term, these go on and on, don't they? B9 is equal to, see, 9 times 2, 18, so negative 1. And D. D, explicit rule, no, does not converge. The limit as n approaches infinity of 17 minus 2n is negative infinity. E does not apply, right? Question 1. One, 3/2, 8, 9 over 4. These are a lot easier to look at as fractions, aren't they? Okay. Let's see. I think it's pretty obvious for multiplying everything by 3/2 now, right? Okay, so let's go with part A. What is the recursive rule? Okay. So A1 equals 1. AN equals 3/2 times AN minus 1. Part B. Explicit rule. AN equals A1 times R to the n minus 1 power, which equals 3/2 to the n minus 1 power, which is equal to 2/3 times 3/2 to the n power.
Why does it equal 3/2 to the n minus 1 power?
A1 is 1, R is 3/2. C. Find the ninth term. A9 is equal to 2/3 times 3 to the 9th power over 2 to the 9th power, which is equal to 3 to the 8th power over 2 to the 8th power.
Could we just leave it like that?
I think, yeah, just leave it like that. D. Does the explicit rule tell us that this converges? So we have 2/3 2/3 to the 3/2 to the n power. These numbers will keep getting larger and larger, right? So. That was 30 minutes. We're almost done. We got this. E does not converge. Does not apply.
Wait, if it applied, what would you do?
You would write the limit. Yep. Thank you very much. You've been wonderful. I hope you have a great weekend.